Hi folks, welcome to the Key Concepts Review for Chapter 2. We're looking at angles here, specifically angles in standard position. If you want to take a look at the disclaimers down below, you'll know what this is for, and maybe some other resources that are available online. Let's dive in. Angles in standard position are measured counterclockwise from the positive x-axis. So if I were going to sketch 72 degrees, I'd draw the grid, and I'd know that right here, this would be 0 degrees. This is 90 degrees counterclockwise. This is 180. This is 270. And when we get back to 0, that's 360 degrees. So if I go 72 degrees counterclockwise, I'm looking at something like this. There's my 72 degrees. If I do 191 degrees, well, I know that's 180 degrees. And then another little bit. There's 191 in standard position. If I do 319, that's past 270, but not yet to 360. So maybe something like this. So those are just some little sketches. Now from there, we can talk about reference angles. They're the acute angles that the terminal arm, which is what this thing is called, the terminal arm, forms with the x-axis. So in the very first one, the small angle that we form with the x-axis, that is 72 degrees. In the next one, we're asking, what is this little angle here? That's called the reference angle, or sometimes written theta r. Now think about it. That's 191 degrees. The first part was 180. We're just looking at what's left over from that. So that's going to be 191 minus 180, or 11 degrees. And you might be able to do that by inspection. Let's take a look at the next one. If we went all the way around the circle, it would be 360 degrees. Now we're only looking for this little reference angle. Again, it's formed with the x-axis, never with the y. So the whole way around would have been 360 degrees. And we want to just take off the 319 from that. When we're done with this, we should always end up with a positive acute angle, an angle less than 90 degrees. So that's the basics on drawing in standard position. Now let's move on to finding some exact trig values. And to do that, we're going to set up some special triangles. This one right here is an equilateral triangle with side lengths of 2 that we can just kind of dream up. So that means this is 60, this is 60, this is 60. I can split that thing in half so that I now have, so I'm just splitting it down the middle, a right-angled triangle. And its hypotenuse would be 2. Its base would be half of the original base, so that's 1. And we could find that last leg using Pythagorean theorem. So c squared equals a squared plus b squared. 2 squared equals 1 squared plus b squared. Work it through, and we're going to get b is root 3. And this is a 60-degree angle. And up top, we would have to have a 30-degree angle, because triangles add up to 180. OK, from there, we can start to talk about sine 60, cos 60, and tan 60. So remember, we have sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. So sine theta is opposite over hypotenuse. If we deal with this 60-degree angle here, then I'd call this the opposite, this the adjacent, and this the hypotenuse. And sine would just be opposite over hypotenuse. Cosine would be adjacent over hypotenuse. And the tangent would be opposite over adjacent, which is root 3 over 1. We'll just call that root 3. Similarly, if we did it for the angle of 30 degrees, well, we have to relabel our triangle. Now, this is going to be opposite. This will be adjacent. And this is still hypotenuse. So the sine of 30 degrees is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And the tangent would be opposite over adjacent, which can be rationalized, if you like, to root 3 over 3. So 1 over root 3 or root 3 over 3. Those are true statements about those angles. And we just proved it using those that special triangle. To find what's going on with 45, let's make another special triangle. We've got a right triangle that is isosceles. And we're going to give it side lengths, leg lengths of 1. And that would mean that its hypotenuse, well, let's see. Its hypotenuse would be the square root of 2. Now in here, both of these angles are 45. Let's label it with respect to this one up top. So this will be our opposite, this will be our adjacent, and this will be our hypotenuse. From there, it follows that the sine of 45 is opposite over hypotenuse, 1 over root 2, which can also be written root 2 over 2 if you rationalize it. Cos of 45 is 1 over root 2 or root 2 over 2. That was just adjacent over hypotenuse. And you can check in your calculators that 1 over root 2 and root 2 over 2 are the same. Tangents, opposite over adjacent. So that's 1 over 1 or just 1. Now, all these special triangles are given to you in your formula sheet, so you can use them on your secondary math assessment. So if we want to find the tan of 60, we would just go to our formula sheet, and I think it's drawn this way on your formula sheet. Gives us root 3 here, 1, and 2. So you'd say, okay, I want the tan of 60, that is opposite over adjacent in that triangle. Must be root 3 over 1 or simply root 3. That's how we can find some of those special values. It's also worth knowing the special values for 0 and 90 degrees. So the sine of 0 is 0, the cosine of 0 degrees is 1, and the tangent of 0 is 0. Sine 90 is 1, cos of 0 degrees is 0, and tan 90 is undefined. And we'll go into why that's the case in a little bit here when we get more into finding trig ratios in standard position. Okay, as an alternative strategy for knowing all these values, you could make a little trig table. You don't have to, but as we move forward, say in grade 12, it may be nice to know these values really quickly. And there's a trick to finding sine, cosine, and tangent in a table like this. Here's what I'm going to do. These are all over 2. These are all the special angles we're interested in, 0, 30, 45, 60, and 90. And all I have to do is go root 0 over 2, root 1 over 2, root 2 over 2, root 3 over 2, root 4 over 2. Those are all the values. Now, some of these simplify. This one is 0. This one is a half. This one is root 2 over 2, and it could also be written as 1 over root 2, doesn't matter. Root 3 over 2 doesn't simplify. Root 4 over 2 is just 2 over 2, or 1. Your cosine row is just going to be sine backward. So 1, root 3 over 2, root 2 over 2, or 1 over root 2, 1/2, and 0. And finally, tangent is just sine over cosine. So 0 divided by 1 is 0. A half divided by root 3 is 1 over root 3. Or you could rationalize it to root 3 over 3. Doesn't matter. The next one, anything divided by itself is 1. Root 3 over 2 divided by a half, that's 2. And 1 divided by 0 is not allowed, so it's undefined. So there might be a couple that you have to memorize in here, maybe these ones. But notice tan is getting bigger as we move to the right. Anyways, you're not required to know this, but it may be a helpful way to organize your sine, cosine, and tan values. Okay, trig values for angles in standard position. So if we're interested in the distance between the origin and some point xy, and we're going to call this r. Notice that this makes a right-angled triangle. And that right-angled triangle has a height of y, and it has a width of x. So from Pythagorean theorem, it would follow that r squared is x squared plus y squared. Or r is the square root of x squared plus y squared. Okay. We might call that the radius for r. And that's going to be the case all the time when we have coordinates in space or in a plane. So if we want the distance between the origin and the point 6, negative 2, 2, 3, 4, 5, 6, negative 2, we're looking for this distance here. We could draw the triangle, or we could just use this property. And maybe we could get away with not even drawing the diagram once we're used to it. So 6 squared plus negative 2 squared. That's going to give us the square root of 36 plus 4, or root 40. And you might remember from grade 10 how to split these apart. That's root 4 times root 10, or 2 root 10. Any of those last three steps are equivalent. But that's the exact distance between here and here. And that's going to turn out to be important because notice again, we've got a right-angled triangle. And if we talk about sine, cosine, and tangent, then we're talking about the ratio of things like opposite, adjacent, and hypotenuse, which will be this r. So if r is the distance between some point and the origin, we can find the trig ratio of any angle formed that contains a point xy. So let's say we've got this angle right here. Its angle in standard position would be whatever theta is there. The cosine is x over the radius, because this is going to be the radius, the hypotenuse. The sine is y over the radius. And the tangent would be the opposite, that's your y, over the adjacent, which is the x. Let's take a look at an example. The point negative 5, negative 12 is on the terminal arm of some angle in standard position. Find all three trig ratios. So this is kind of a classic question. Here's negative 5, negative 12. Maybe I'll draw that a little better to scale. Okay. Here it is down here. If I want to find all three trig ratios, I need to figure out what r is. So r is the square root of x squared plus y squared. That'll be negative 5 squared plus negative 12 squared. Notice that r is always going to be positive because we're squaring some values in there. It's the square root of 25 plus 144, which is the square root of 169, or 13. From there, we can find all these trig ratios. The cosine of this angle, theta, is going to be x value, which is negative 5, over the radius, which is 13. Okay, so I'll just show where that came from. X over r. The sine for this angle is y over r. So that's negative 12 over 13. And finally, the tangent is going to be y over x. Well, let's see. Y here is negative 12. X is negative 5. Negative divided by a negative gives us a positive. From this, some properties emerge. We know that r is always positive. So that means sine is going to be positive whenever y is positive, because sine is just y over r. And y is positive in quadrant 1 and quadrant 2. So if we're wondering what's positive, sine is positive here, and it's positive in this quadrant. Cosine's positive wherever x is positive. Well, x is positive in quadrant 1, and quadrant 4. So cosine is positive here and here. Tangent's positive wherever x and y are either both positive, which would give you a positive, or both negative, because negative divided by a negative is a positive. So that happens in quadrant 1 and quadrant 3. So that's where each of our ratios are positive, and then if they're not positive in a quadrant, clearly they're negative. The easy way to remember this is A, S, T, C. A whole bunch of acronyms that come from that. All silly turtles crawl. All students take chemistry. Some people call it the cast rule. I don't like that because it doesn't start with quadrant 1, but you could work that way as well. But it just answers the question, what's positive? They're all positive, or sine is positive in that quadrant, sine, or tangent in this quadrant, or just cosine in this quadrant. Before we go and find some ratios for any angle in standard position, or any special angle in standard position, we want to look at these quadrantal angles. So those are the ones at 0 degrees, 90, 180, 270, or 360. And to find what the ratios are, we could just make a point here. And we might as well make the easiest point possible. Let's call this 1, 0. And at 90 degrees, we could have 0, 1. And at 180, we could have negative 1, 0. And here we could have 0, negative 1. Now, whenever we do that, we're talking about a radius of 1. This is just a length of 1. So if we look at those special points, well, x over r is going to be cosine, but r is just 1. So from here, you could say that, okay, well, the cosine of 180 must be negative 1. Y over r would be the sine, but again, r is just 1. And y over x is the tangent. And that gives us an explanation why tan 90 is undefined. If I tried to do tan 90 here, I'd have my y value divided by my x value, undefined. You can't divide by 0. Find all trig ratios for 180. Okay, so let's start with cosine. It's just the x value of this nice little point. The sine of 180 is the y value of that little point. And then the tangent of 180 would be the y value divided by the x value, or 0. Okay, we're basically using this little point. Any point that shows 180 is going to work, but it's easiest with a radius of 1. Okay, last piece of the puzzle here for angles. When we're looking at trig values for angles that are multiples of 30 or 45, we can find them easily. We need to sketch. We need to find theta r, or the reference angle. We'll use either special triangles or the table to figure out the appropriate value, and then we're just going to correct for whatever quadrant we're in. So I'll show you what I mean here. If I have sine of 150, I'm going to draw 150. It's 150 degrees counterclockwise. Now I have to figure out what the reference angle is. That's this thing here, theta r. Okay, if I went all the way to the x-axis again, that would be 180 degrees. So what's missing must be 30 degrees. So again, theta ref here is going to be 30 degrees. I need to know what the sine of 30 is. And since I've got my table here, I can tell that it's just a half. Or if you were to take the special triangle that's in your formula booklet, or your formula sheet, it looks like this. You can figure out that the sine of 30 is 1 over 2. The last piece of the puzzle is to make sure that we correct for what quadrant we're in. So A, S, T, C. We're in quadrant 2. Is sine positive there? Yes, it is. So the sine of 150 is positive 1/2. Let's try another one. Cos of 135. I'll draw 135. I'll find my reference angle, so that's going to be 180 minus 135. Theta ref here is 45 degrees. So that means I need to know what the cosine of 45 degrees is. Again, I could either use my table or use special triangles. It doesn't matter. So if I use a special triangle, there's 45 degrees. This is root 2. Cos of 45 is 1 over root 2. So I say, all right, cos of 135 must be 1 over root 2. And then I have to think about what quadrant I'm in. ASTC. I'm in this quadrant here. It says sine is positive there. Cosine is not positive, though. So if cosine's not positive, we must have a negative here. We're just checking to see whether it's positive or negative in that quadrant. Let's take a look at one last one. We want the tan of 300. So I'll draw the angle. It's going to be 360 minus 300, or a theta reference of 60 degrees. I ask myself, what is the tan of 60? I can use either the special triangle or my table to figure it out. The tan of 60 is root 3. And again, we've got A, S, T, C. We're in quadrant 4. So tangent is not positive in quadrant 4. So the tan of 300 is root 3, but it's got to be negative because of the quadrant we're in. We might also be asked to do this backwards, so find the angle given the ratio. And it's very similar. We're going to find a reference angle. We're going to sketch in the appropriate quadrants, and then we'll write our angles in standard position. So over here, I have sine theta is root 3 over 2. And I'm wondering, what are all the angles that have that property? Well, first of all, a sine of root 3 over 2 is an angle of 60 degrees, which I could, again, also have done by taking a look at the triangle, special triangle, and saying, oh yeah, for 60 I've got opposite over hypotenuse of root 3 over 2. However you do it, you need to come up with that reference angle. And now we have to notice it's positive. Well, where is sine positive? It's positive in quadrant 1 and quadrant 2. And we're looking at theta reference of 60 degrees. So the last thing we have to say is, well, what are those actual angles? One of them is just that 60 degrees. Not theta r, but theta, the actual answer. And the other possibility is this one over here. Now that is 180 minus a 60, or 120 degrees. So we're thinking there 180 minus 60. Those are the two angles that satisfy that equation. So there's more than just one. We have to be aware of that. Let's try another one. Cos theta is negative 1 over root 2. So the reference angle is going to be 45 degrees, either by triangles or by the table. Now we're saying cosine is negative. So where is cosine negative? It's positive in quadrant 1. It's negative in quadrant 2. It's negative in quadrant 3. And it's positive in quadrant 4. Each of those have reference angles of 45 degrees. Now that we've got that drawn, it should be easy for us to figure out the actual angles that have this property. Okay, so we'd have the first one is 180 minus 45, which would be 135. So I'll just put that thought bubble below it. That gives us this one right here. And the other one would be 180 plus 45. It's just a little bit beyond 180. Those are the two values. Now, if we weren't sure, we could go to the calculator and check. Are they right? I'll make sure my calculator's in degree mode. And I'm going to put in the cosine of 135. And it gives me this messy number, negative 0.707. I'm not sure if that is negative 1 over root 2, but I could check. I'll type negative 1 divided by square root of 2. If it's the same, then I must have done it right. Yep, 135 is good. Oh, let's check 225 as well. Yes. Okay, so we always have an opportunity to check if we have the calculator. Very last one. Tan theta is root 3. So that means we're talking about a reference angle of 60 degrees. I'm going to sketch it. It's positive, so tangent is positive in this quadrant. And it's positive in quadrant 3. That's where you have your T. What are these actual angles? Well, they're 60 degrees and 180 plus 60, or 240. Having that sketch is really going to help us. Hope that you found this helpful. There are downloadable notes below if you'd like, and good luck.